Okay, after some multiple technical difficulties, I guess, I think I have everything ready. So what I'm going to talk about is molecular replacement and crystallographic refinement, which are two techniques that can be used once you've either gotten an entire diffraction data set, or you have a diffraction data set and or a full amplitude data set from images that goes to atomic resolution, where you can start to actually use chemistry to do some of the work for you to refine where your atoms are within the structure. So the two ways to obtain phase information from 2D crystal structures are to measure the phases directly from images. No matter what protein you have, if you can collect enough images at high enough tilt angles, at high enough resolution, you can build an atomic model. This works regardless if anyone has ever studied the protein before or not. However, this is very time-consuming and rather difficult to do. On the other hand, if there's a high-resolution structure of a closely related protein, you can use indirect methods, which allow you to, rather than collecting these images to get the phases, you can just take the phases from someone else's structure. This has been done for many years with X-ray crystallography, but it's somewhat less used in 2D crystals, mainly because there's not a whole lot of crystals that diffract to high enough resolution where you can use it. But it's a very powerful tool and can allow you to collect enough data in a year or two to get a whole structure, rather than the 5 to 7 years that we've heard about previously to get enough tilted images to get the phases, particularly at the high tilt angles. So what happens once you've got this map, either if you've got it from collecting phases from images or you've used molecular replacement? How do you turn that map, which is just a bunch of blobs, at higher resolution? The blobs have a little more features, but at 3 angstroms, 3.5 angstroms, those blobs are still pretty blobby. How do you actually turn that into a structure? So the first thing you do if you have a novel protein is you have to build the backbone. So you have to go carbon by carbon and actually start to build the protein into the density you have. The side chains can start to guide you, particularly if there's a big one like a tryptophan or a phenylalanine, but it's pretty difficult. If you're using molecular replacement, it's a bit faster because you already have an initial chain that's been traced in, which is what you got, which is how you built the phases. So this way, what you have is an initial model. It may be wrong, it may be poor in some places, particularly the differences between the protein that you used as your search model and your actual protein, but you have a start to work with, and so you can start to go through and look for areas that are wrong, delete those, and then manually rebuild them yourself. So this is a much faster way. Both methods require a lot of work, though, to take your model from this initial model, the initial map, and improve it, and this is what is known as crystallographic refinement. And the advantage of these steps is the X-ray people have been doing this for decades, and the software is fantastic. It's extremely user-friendly. If you need to do anything, most people's department have a few crystallographers in there. You can go and ask them, and they can tell you how to do anything. Though even easier, a lot of the programs, you can just use Google, and there's mailing lists that are thousands and thousands of entries long that can tell you, I have this problem, what do I do? Type it into Google, and odds are someone at some point in the past has had the same problem, and we'll give you a pretty good description of how to do it. So the first thing I want to talk about is molecular replacement. So if you have 2D crystals that are big and well ordered and you can collect the fractions, what do you actually need to do to be able to use molecular replacement to get your initial phase map? The first thing is obviously a complete merged diffraction data set. The higher the tilts are, the better, because you're going to have sampled Fourier space more completely, and thus you'll have a more accurate position of your Patterson function, which is the way that molecular replacement actually finds where your protein is in Fourier space. So we usually try to get diffraction patterns of 60 to 70. You can get away with sometimes a little bit less. More is obviously better. It makes your life easier. Your initial map will be cleaner. And then the other thing you need is a high-resolution structure, so atomic structure of a homologous protein. The numbers usually say that you need about 1.7 angstroms RMSD between what you expect your protein to be and what the homologous structure is. And you also need somewhere between 20 and 40% identity, depending on how conserved the protein is. Sometimes you can get away with a lower identity if the proteins have a very similar fold. If it's a less similar fold, and you can, the advantage of 2D crystals is if you have a 7 angstrom map from images, you can have a pretty good idea of how well the protein is going to fit into this density map, and so you may be able to get away with something that's a little less identity. The other thing you need is about 30 to 40% of your total density needs to be made up of protein sequence that you know. So if you have a protein that has a large transmembrane domain, a large extracellular domain, and one of those two has been solved, you can possibly use the part that's solved to obtain the phases for the whole structure, and then use that to build up the rest of the map. So in that case, if someone has been able to crystallize the extracellular piece, and you have the crystal or the 2D crystal of the whole one, and you can get diffraction, you can use the extracellular piece to solve your phases initially, and that'll allow you to start to build the transmembrane domain. If you have any questions, please stop me during this. This is supposed to be informative. It's something that is useful, but not necessarily all that often done in 2D crystals. So if I'm not clear or if something hasn't made a whole lot of sense, please stop me and I'll try to explain it in a little more detail. And then this is the protocol that we use in our lab. Every lab does it a little bit differently. There's maybe a half dozen or more programs to do molecular replacement. The one that I use is called Phaser, and it works very well. It uses a maximum likelihood scoring function, which from what I've heard from people who spend a lot of time looking at these things, tends to be more accurate and will find you the answer even if you have a slightly poor starting model. With aquaporin 0, I don't really have that problem because I'm starting with the same protein. But if you were starting with a protein that was fairly far off, Phaser may work better than MoleRap or Mr. Bump or some of the other ones that use a different scoring function to try to find where your actual solution is. So like I said before, you need a merged diffraction data set. You need it in MTZ format, which IPLT will, when you finish merging, it produces that. Same with if you use some of the CCP4 tools after you've finished merging your data with the MRC programs. You need a search model in PDB format, and then you need a space group determination. Space group determination is necessary so you can know how many copies of your protein should be in the unit cell, as well as the mass that the program is trying to find to fit the density into within that unit cell. So the first step is to convert your intensities into structure factors. So diffraction, you get everything as the square of the amplitude. So you need to use a CCP4 program, Truncate. There's a few other ones that work, but this is the one that I use to convert intensities into structure factors, which are then useful in the rest of the programs. Another thing that this does in the background is it can uniquify. So when we collect diffraction, we don't collect all the Fourier space. There's the so-called missing cone. And you need to have values there, even though you don't actually measure them. The programs want you to have a particular value, even if it's just a null value, so that it doesn't start looking for things that aren't there. So even if anything along the 00L line that we don't measure, it'll just put a question mark so it can find it, even though there's nothing there. The next step is to use Phaser to actually solve the molecular replacement structure and give you your initial phases. And then after that, you can go into a molecular graphics program. I like Coot. O also works well, and there's a few others, but this way you can quickly go and directly look at your map and look at the solution and see if it makes sense. This is where you can really get a good result. There's a lot of numbers that you'll get from Phaser, but if you can look at your map and it starts to make sense, odds are you found the right solution. So what are the tools that we use? CCP4i, which is the interactive version of CCP4, which people have talked about how 2DX calls some CCP4 functions, as does IPLT. CCP4 also has its own interactive GUI that you can use, and it's very intuitive. It's pretty straightforward. It doesn't take a whole lot of time to get used to it. It's point and click. There's a very good help online to go through, and so on this side you have the program list. There's probably 100 programs that are there for different tools that you may need. And then these are your individual runs, how many different things you run. So the first thing you can see here is I ran Truncate and then Phaser, and then I ran RefMac with a rigid body refinement just to see if it looked right. And I did this over and over again as I was moving to higher and higher resolution during my refinement, just to make sure that my refinement was going properly and I wasn't starting to introduce too many artifacts during it. Okay, so what do all these files look like? An MTZ format, which you can dump directly from 2DX, or if you have a diffraction data set, you can go into CCP4 and that'll show it. It's a binary file, so you can't just open it directly. You need to use a tool like MTZ dump or 2DX, which will convert it into an ASCII file that you can actually look at. And a file from a diffraction data set looks like this. You have 5 columns for the 5 different values. You have an H, a K, an L, an I mean, and a sigma I mean. So this is your intensity, and this is how much error your intensity thinks it has. So you have a whole list of these reflections for everything that you've measured, and then the intensity, and then the errors. So you can see that some are much higher than others, as we know from looking at the plots that Andreas showed earlier, that there's a strong oscillation. So some intensities are going to be very high, some are going to be weak. And this is how you actually start to solve your structure. This is done, you can use RotaPrep or F2 MTZ or a few other programs that can convert your HKLs from every single image or every single diffraction pattern into one merged pattern or one merged list, and this is what this is. The next thing you need to do is create a search model. So what is a search model? The search model is a PDB format, which many of you I'm sure have looked at, of what you think is a homologous protein. And what you need to do also is you can't just use a whole protein, because odds are there's going to be differences between your protein and the protein that you're trying to solve the structure of, which are what usually makes it interesting. If you were solving the same protein over and over again, odds are it's not going to be quite as interesting. So the ways that you usually do it, since we mostly work with membrane proteins, is you want to start to cut off the loops. Loops tend to be the least well ordered in 2D crystals, and they also tend to be the most variable. So what you can do manually or in a GUI is just go through and find the residues that are in a loop and just delete them. And you can do the same on both sides. And if there's any region that you know is very floppy or very flexible, or from biochemistry you have a pretty good idea is going to be different, you can also delete that. And that way you have less differences between what your search model is and what your final structure is going to be. And then the last thing is to find the space group. And people have already spoken about all space, so I'm not going to continue. It's just you look to find the solution. You want to have a pretty good unambiguous solution from all space. I usually think that 5 or more good 0-degree images, so somewhere around 5 angstroms or better, will give you a pretty good idea of what your phase residuals should be. And you want to compare it to the target. So you can see here this one is 16.1 and the target was 16.5. So this is most likely a P121 crystal. The next step is to convert the intensities into structure factors. And I'm going to try to actually show you how I do this so that if you ever need to do it on your own, there's somewhat of a demonstration. There's many good examples online if you look up crystallographic refinement or molecular placement. But for coming from electron diffraction, it's a little bit different. There's not very many examples that are published of how to do this. So you use the CCP4 GUI, you open up Truncate, and then you want to ensure that you have unique data, and you also want to add the free R column. The free R column I'll go into a little later, but that's how you can tell during refinement if you're getting the correct solution or if you're starting to introduce artifacts into your solution. Here are some of the other ones that are important. This is your MTZ file of your merged intensities. This is what's going to be your structure factors. These are the number of residues in your asymmetric unit, so it tells the program about how much scattering power you should be producing from your diffraction intensities, your space group, your unit cell, and then the resolution. If you're not sure exactly how good your data is, you may want to cut back on your resolution and not use all of it for molecular placement. And then the output from this program is very similar to the intensity file, but rather than intensities, you now have structure factors. And the other thing you also have is this column here, which is the free R column. So I use a 10% free R. If you have a lot of reflections, you can maybe use 5%, but it's just about 1,000 reflections that you exclude from refinement. If you only have 3,000 because you have a lower resolution structure, you may use a few less, but the idea is that you want to have as many reflections as possible out of your refinement to kind of tell you if you're refining properly, if you're starting to go off. And so that's what these are. Anything that has a 1 flagged here would be in the free R. Everything that's 2 through 9 or 0 to 9 that's not 1 would be refined against.
In the data that you use, do you include all the low order data as well, or do you exclude that?
In diffraction merging, because of the beam stop, I usually block out anything from below about 20 angstroms. So that's where most of the solvent effects are. But during refinement, I don't exclude any particular data, also for molecular placement. Any other questions? Okay. And so another thing you get, because you've uniqueified your data, you've tried to fill in the missing cone even though you're not adding data, it's just blank values, is you can start to see how much of Fourier space you're sampling. So you can see here that of the, what is it? There's about 3,000 reflections out of 8,000 or 5,000 that are missing. So that's about 84%. Math doesn't work right, but it's 84%. So there's about 15% of the reflections to whatever the resolution limit is here that weren't sampled, and so it had to add just this question mark for them. The next thing is phasor, and again, it looks very similar. All the programs for CCP4 look like this. That's why I said that after a few days of using it, you'll have a pretty good idea of what you're doing. It doesn't take too much to figure out that, okay, so again, we add here the input MTZ file. Here is our search model. Here is the criterion for this rotation. So this is actually how you figure out what is the best solution. For molecular placement, what you tend to do is a two-step search. The first thing you do is a rotation search, and then the second step is a translation search. I'm not going to go into detail into how it actually works because I'd probably get it wrong, and there's people here that can probably do it better, and if not, you can ask any crystallographer, and they do a great job of explaining it. And then the last thing that you need are the number of components in your asymmetric unit and then the molecular weight of your protein. And then this is the reference. I have the references for most of the programs I use here. If you want to go back and read in more detail how they actually come up with this, it's how they produce their maximum likelihood scoring function, or any other ones, how they produce the scoring function. So some additional considerations in case you're having issues, you're not getting a very good answer. Is what you could do is break up your protein into two pieces and try to search for each of those pieces individually, particularly if you think that you have a flexible domain that may have a hinge. You may want to guess where that hinge is, cut it at that hinge, and search either sequentially or just two separate pieces to try to find those, and that may give you a better solution. And the other thing is if you have a protein within a family where there's multiple structures that have been solved, you may want to use all of them and try to find which one gives you the best solution. So what are the outputs from phasor? Phasor, you have these scores at the top of your log file. So similar to 2DX and MRC, there's log files. If you look at them, you can find a lot more information about if something worked. So these Z-scores are actually how they tell you if it worked or not. This is the rotation function Z, so this is just trying to search all of any possible rotation in Fourier in Patterson space, and then the translation is when you move it to your actual position. So this is a Z-score of about 35. Anything over 10 is very good. Anything over 15, you're almost certain that you've got the solution right. The next thing is this packing score. So are there any clashes between multiple copies of your protein in the unit cell? If you have a large packing error, then odds are your solution's not right, because there's no way that you could have two subunits in the same exact place in your structure. And then the last is this log likelihood gain score, which is what phasor uses to try to score. And then down here, there was just one solution. If you have multiple solutions, you may get multiple copies of this. Sometimes it can just be rotations of the same thing within your unit cell if you have symmetry that you made a mistake with, and then you may want to go back, check your symmetry, and rerun it again so that it finds the proper number of copies. And then these are your output files. So you have, again, a PDB. You have an MTZ, which this now has phases, so you can immediately convert this into a map that you can look at, and then a solution file, which tells you how it found this PDB, what the rotation and translation were to get this. And then now going into COOT, which here's now the citation. This is a great molecular graphics program. It's really also very simple to use. It's associated with CCP4, so anything you do in CCP4, it's very quick to bring it into COOT and look at it. The first thing I always do is check the C alpha trace to make sure that it looks right. So you can see as you follow the alpha helices down, the density follows those. Before you start looking at side chains, you just want to make sure that the alpha helices were traced. Particularly if you have large differences, a lot of the side chains will be different, but the positions of the C alphas should be fairly similar. If this looks good, then what you can do is add the side chains and see if it really makes sense. So continue to look and start to look for true differences. So here's an example of a region where the molecular placement structure was actually quite different than with the final structure. This is the loop A that Tom showed the other day that is shifted over to fit into the lipids, and you can see that there's no density in this region for where the old version was. So I had to take it apart and rebuild it into the density that was there to make it a more accurate model. Yes, Tom? Blue is the 2FO minus FC map, which is what you consider to be your density map. Green is your FO minus FC positive, so this is places where there should be density, but you don't have density in your model. Red is the minus version of that, so where you have density, but there shouldn't be. It doesn't always work out exactly like that. You can see that there's a red blob here, but there's nothing around it. Because every atom in real space affects everything in Fourier space and vice versa. So you can't necessarily just say that there shouldn't be anything here. Maybe to get rid of this, you need to move something on the far other side of your protein. So what are some potential issues that you can have from using molecular placement to solve your structure? If you have poor results with a good search model, you may want to try to reduce the resolution. With phaser, it tends not to be so resolution dependent. Even the difference between 2 angstroms, 4 angstroms, phaser only uses data that it thinks it's the best and so it will find it regardless of your resolution. Some of the other programs tend to be more resolution dependent, and you may need to cut your data at 4 angstroms, which for electron diffraction is the best because that's where your best data is going to be, and exclude the higher resolution data until you start refinement. Alternatively, as I said, you can start to cut your search model into pieces, particularly at a flexible hinge, and put those two together to find your position in the density or in Fourier space. And then the last thing, which is really important for molecular placement, is this issue of model bias. Because as we've shown time and time again, phases mean a whole lot more than amplitudes, and using the phases from something else, you can make, with just about any set of amplitudes, if you work hard enough, your density look like another protein. So what you need to do are things like omit maps, and there's a few other tools that can be used to start to remove the initial phases so that it puts more weight on your amplitudes to try to push you out of that initial well caused by the initial phases of your search model. And so now you have your search model. What's the next thing you want to do? You want to build your structure. So what crystallographic refinement is really improving the phases so that you can get better and better maps, and thus your model and the map fit more and more closely because your amplitudes are fixed, but the phases around them you guessed at from your molecular placement, and they can be way off because they weren't measured. And as you refine, they start to get better and better, and so your model should agree more with your amplitudes. One thing that we have to be careful of is electron crystallographic data is rarely sampled beyond 3 angstrom. So a true atomic structure where you have 3 points for every single atom is rarely determined. You don't have enough data to sample everything completely. So what you have to do is start to use restraints. So rather than 3 or 4 different unknowns for every atom, maybe you start to restrict your bond lengths and bond angles in stereochemistry, so that a whole alpha helice is maybe a few parameters rather than a few thousand parameters, which you just aren't going to get enough data to do. And so all of the crystallographic refinement programs have these built in. You can change the weights on these, and if you think that you're starting to get errors because it's over refining, you can raise the weights on your restraints, and this will start to dampen the way that it's trying to fix even the planarity of a phenyl group. And then at the end, the correctness of a model is evaluated by looking at the R-free and then the Ramachandran plot, which are 2 things that are excluded from refinement that you can check at the end to make sure that you've been going in the right direction. And then one last thing is if you have experimental phases that were obtained from images, you can use these as an independent check on the quality of your structure. So you can look at the phase residual of your merged images on the final structure, because your phases from images are only used in the initial model. Once you start refining, you're moving further and further away from those, and so they're not going to be part of the parameters for the refinement program. And then the 2 main programs for refinement are CNS and RefMac. They're both quite good. I use CNS just because that was what was used previously in our group. RefMac also works quite well. And what they are is they're iterative processes. So the first thing you do is run a round of restrained refinement where you tell the computer, try to make the amplitudes look, the F-calc look more like the F-observed, so your observed amplitudes and your measured and the expected amplitudes. And so you can see each time it makes it a little different. So some of the C alpha trace here is a little bit different because of refinement. And then on the other side of that is you actually manually make some changes. So you start to look for regions in your protein that are large errors. Large errors aren't going to be fixed by these very small changes by the refinement, and such as this side chain that needs to be flipped. And so you can see now it fits better. Refinement will find its true location over a few rounds. And the last thing is the R-free. So what is this R-free and why is it important? What it is an independent, unbiased measure of the correctness of a model. When you start out, you have this file of maybe 5 or 10 or 20,000 reflections, and you exclude a certain number of those from refinement. And by doing that, you make sure that they're not refined against the data, so that when you can be at the end, you can say, yes, these have gotten better during refinement, so my refinement's going in the right way. It doesn't always work, but most likely, if you start to refine something that's incorrect, your R-free will stay the same or go worse or get worse during refinement, while the crystallographic parameters that you're actually refining against will get better. And then some additional considerations for refinement. If you have non-crystallographic symmetry in your crystals, which we've seen a few examples of, if you have a 5-fold symmetry which cannot be crystallographic, then what you can do is start to use the knowledge of how that if you have 5 monomers, they all have to look the same. You can tell the computer that the phases of those have to make the density look the same, and there's quite good programs that can do this. There's also cross-crystal averaging, where if you have multiple crystal forms of the same protein, you know that even though the amplitudes are going to be different because they're different crystal forms, the maps have to look the same. And so you can use density modification to start to say that these 2 maps should look the same, and that'll start to restrict the phases. And then one last thing is solvent flattening. So as we've seen before, the envelope that we've decided, so how big the protein is going to be smaller than the asymmetric unit cell. So there's going to be empty volume in there. And we can tell the computer that in those spaces, the density should be much lower than the density of the protein. And by doing that, we can start to restrict the phase space, and this will improve the quality of your map. And then the last thing is that if you have a very high resolution structure, scattering factors for 300 kilovolt electrons are slightly different than those from X-ray diffraction. And so if you use those, you can start to improve the quality of your maps as well. And then last thing is there's all these other software packages. If Phaser isn't working, maybe you can try a Moray or Mr. Bump or MolRep. And if CNS isn't working, maybe RefMac. Or there's a whole lot of tools that can be used because there's so many more people that are developing tools for X-ray crystallography than there are for 2D crystals, just because it's a much larger field. And try to take advantage of these tools. And also, if you have problems, Google's your friend. The crystallographer down the hall, they know a lot. You go and take advantage of that. And then lastly, here are some references for some of the different software packages and some experimental examples of people that have used molecular replacement to solve electron diffraction structures. And then here's a good course online. If you want more details on the theory of molecular replacement, you can go back and look at it. And then lastly, I'd like to thank the people in my group that have helped me a lot with this, Tom, Andreas, and Zhongli, our EM manager, and then particularly for the electron diffraction data collection that I described the other day. I learned a lot while I was in Fujiyoshi's group in Japan, and particularly from his postdoc, Kazuhiro Abe. Thank you.
Thank you very much, Richard. Any questions?